Hi, everybody. So in this video, we're going to talk about hematopoiesis. So uh, before we even start talking about hematopoiesis, let's look at the word a little bit. So hema is going to be blood, poiesis is going to be to make. So in this case, we're going to be making blood cells. Okay. Now we're going to split hematopoiesis really into three major types. We're going to have erythropoiesis, thrombopoiesis, and leukopoiesis. Each of these is already kind of telling you what they're doing, if we can remember what the different cell types were called. So leukopoiesis, so leukocytes. So this is how we're going to make leukocytes. Thrombopoiesis is how we're going to make thrombocytes. And then erythropoiesis is how we are going to make our erythrocytes, or our red blood cells. Now, hematopoiesis is going to start with a special type of stem cell. Okay, so a stem cell is simply a cell that can grow into multiple different cell types. It hasn't yet differentiated. So it has the ability to turn into lots of different things, depending on the instructions that you give it. So the enzymes that you hit it with, or vitamins, or whatever it may be, or just different environments, it can differentiate into different types of things, and lots of different types of things. So starting with our hemocytoblast. So hemo, blood, cyto, make, blast. So hemocytoblast. So it's a cell for making blood cells. So it makes sense then that this would be some type of stem cell. Okay. Now, our first decision here is whether or not we're going to push it into what we call the myeloid line or the lymphoid line. Okay. Myeloid is going to be active cells that are actively doing things now. Okay, our lymphoid lines are going to be cells that will be kind of activated later on. So sometimes they're somewhat asleep, I guess you could kind of say. Okay, at least some of them will be. They're still going to be cycling around, but they require a trigger to go into specific types of activities. Okay, now let's go ahead and start with our myeloid line. So we're going to push our myeloid line over here, and it's going to have a myeloid stem cell. Now, our myeloid stem cell can be then triggered by our multi-CSF to push us into one of three directions. We can either make a white blood cell, a thrombocyte, or a red blood cell. Now, let's talk about red blood cells first. So red blood cells under this trigger called EPO. So EPO is a hormone called erythropoietin. So erythro, red blood cells, poietin, make. So this one triggers the production of red blood cells. So we're going to trigger the production of red blood cells. Now, keep in mind that all of these processes are happening in the red bone marrow, in primarily our axial skeleton and in the heads of our long bones, particularly our humerus and our femur. That's really it. So it's axial skeleton and then the heads of our humerus and our femur. Now, EPO as a hormone is going to turn that myeloid stem cell into what we're going to call a progenitor cell. And we're just going to kind of work our way down. Under influence of additional EPO, we can then turn into these erythroblasts. Well, erythro, red blood cells, blasts to make. And then eventually we are going to become this normoblast. Now, the normoblasts are kind of fun because this is actually where we are going to get rid of the nucleus. Because one of the interesting characteristics of our red blood cells, remember, is that they are anucleate. They do not have nuclei. Now, they don't have nuclei, so they can have this little biconcave shape. That biconcave shape makes them really good at moving through blood vessels, and particularly allowing them to stack up like quarters in our capillaries so that we have really efficient gas exchange. So how do we get rid of the nucleus? Well, we're going to get rid of that nucleus here at this normoblast stage. So we're going to trigger this release using some sort of genetic pathway. Now, after this, we will then become a reticulocyte, and then finally our erythrocytes. So if you were to say give a person more EPO than they ordinarily make, you would increase the amount of red blood cells that this person is doing. Now, or that this person is making. So because you're going to kind of force this cell now down this line and encourage the production of additional red blood cells. So you're going to make this person's blood thicker. So you would raise their hematocrit percentage. Make their blood thicker, allow them to carry more oxygen. However, it makes their blood thicker, which makes their heart have to work harder to move this blood through the systems. However, this process is actually called, or sometimes called, blood doping, and was actually really popular back when Lance Armstrong was competing in the Tour de France. He was able to win a lot of those Tour de France's. However, he was utilizing, as was most of the field, admittedly, back then, utilizing EPO injections to increase their be important in this process here. Additional testosterone in the system will lead to additional erythropoietin, which will then by extension lead to additional erythrocytes. So someone that is taking steroid injections, for instance, will have an increased volume of erythrocytes as well, because we're pushing it down this line. Now, importantly here with erythrocyte formation, so erythropoiesis in general, we do have a few things that we need that we may not have, that you may not always have access to. Primarily, we are going to need iron. If you've ever heard of someone that is anemic or know someone that is anemic, this means that their percentage of red blood cells is fairly low. So we need to raise their level of red blood cells. One of the ways that you can do that is giving them EPO. However, we still have to have the important functional part of our erythrocytes, and that is the protein hemoglobin. Without iron to bind oxygen, or without iron, our hemoglobins don't work correctly, and we can't really make hemoglobin without it. Because we have this little heme group in the center with a little iron molecule right in the middle that oxygen is going to bind to. So you have to take in a whole bunch of iron in order for us to produce all of these erythrocytes. This is also why, if you've ever tasted blood, blood has a very kind of irony, metallic-y taste, and it's because of all the iron that is necessary. So if someone is anemic, oftentimes you will need to give them additional iron in their diet to help them produce more red blood cells so that they can raise that hematocrit or that erythrocyte percentage. Now, next we will talk about leukopoiesis. Now, leukopoiesis is either going to come from our myeloid stem cells or our lymphoid stem cells. Lymphoid stem cells will turn into either lymphoblasts, will either turn into B lymphoblasts or T lymphoblasts, depending on the particular lymphoid line. And these are then going to become our T lymphocytes, B lymphocytes, and our natural killer cells, or NK cells. These are all going to be very important in our immune system, and particularly dealing with our immunoglobulins and things like that. Now, next we will talk, we've got our progenitor cells, so the progenitor cells up here. But under G, CSF, so G for granulocytes, we can go ahead and push that progenitor cell through our myeloblast stage into our different types of granulocytes, so either neutrophils, basophils, or eosinophils. Our monoblasts are going to be given this MCSF, and that's what's going to push them down to their particular chain. Now, over here in thrombopoiesis, we're going to have something be a little different. Here, we're going to have this specialized cell that we're going to call a megakaryoblast, and it's going to become a megakaryocyte. Mega meaning large. So these cells are huge. Notice that your white blood cells are just barely larger than your red blood cells. So this way they can still pass through the blood vessels and things fine. Megakaryocytes, not so much. Megakaryocytes actually don't have to pass through the blood vessels, so they're going to be really large. But I also want you to pay attention to these little feet-like projections that we have sticking off of our megakaryocytes. So when you give this megakaryoblast additional thrombopoietin, you can actually push it to develop further into these megakaryocytes. And we're going to produce these little feet. So now we get this awesome squid-looking thing with these really long arms that reach down into the blood vessels. Now, by reaching the arms out into the blood vessels, well, what's going to happen in the blood vessels? Well, blood's going to be flowing through them. And if you've ever listened to blood flow through an artery, or you just can listen to your heartbeat, you're pushing a lot of stuff through there, and it's happening fast. So there's a little bit of force as these things are moving through the blood vessels, and just the force of the flow of the blood. So just like a water hose. Okay, so with this water hose of water pushing past it, it's going to cause these little tiny pieces of these cell membranes, or these extensions of cell membrane and extensions of the cell, to break off. So as these little fingertips reach down, they just get broken off, and they secrete keep making more, so that you can continue shearing off the tips of these little squid feet. However, the tips of these little squid feet are going to be our platelets. The squid arms themselves we're going to call proplatelets, pro meaning before, so these are prior to them becoming platelets. But then they get sheared off, and they are just platelets from that point on, so they're going to continue to do all the jobs that platelets are going to do. And this is once again happening in the spongy bone of our bone marrow. Now, if you have any questions about ways that blood cells are produced or their lifespans or anything like that, please just let me know, and I'll see you in the next video. Thanks. Bye.